Hi, and welcome to this AWS webinar. Today, we're going to explain how you can enable up to 40% better price performance using AWS Graviton2 based EC2 instances. I'm Jeff Underhill. I'm part of the EC2 business development team. With me presenting today, I have Arthur Petitpierre, who is a specialist solutions architect, and we also have Sudhir Raman joining us. Sudhir is a principal product manager, and he'll hang around and join us for the Q&A at the end of this webinar. So let's jump in. So AWS wants to ensure our customers have an EC2 instance to run virtually any workload and meet any business need. As a result, we have a variety of EC2 instances in different categories with different capabilities and storage options, ranging from general purpose through to graphics intensive, choice of process architectures, high frequency processors, instances with large amounts of memory, large amounts of networking. We want to be able to run pretty much any workload people want to host in AWS Cloud. Part of that choice includes the broadest choice of processors. We have a variety of instances based on Intel Xeon Scalable processors. At the end of 2018, we introduced EC2 instances based on the AMD EPYC processors. And also at the end of 2018, we announced the AWS Graviton processors. That's going to be the focus for our discussion today. So AWS Graviton processors are custom AWS silicon built on 64-bit ARM Neoverse cores, but with custom designed silicon by AWS. This is targeted with optimization specifically for cloud-native workloads based on AWS's history of running a multitude of workloads in the cloud over decades. This also allows us to rapidly innovate, build, and iterate on behalf of you, our customers. So the very first instance powered by AWS Graviton processors is the Amazon EC2 A1 instance. This was announced at reInvent in 2018. It's optimized for cost and performance specifically for scale-out applications, provides our customers with significant cost savings, and it's based on 64-bit ARM Neoverse cores and custom AWS silicon. The target applications include web tier, containerized microservices. We've also seen this attractive to people developing software targeted in the ARM architecture who want to implement a native build and test environment CI/CD pipeline. These instances come in 6 different sizes with up to 16 vCPUs and 32 gig of memory, up to 10 gigabits of networking. There is also a bare metal option, and they're available in 9 regions today. Here's Andy Jassy at reInvent 2019 on stage talking about the customer and partner adoption we've seen for that first generation AWS Graviton-based instances. So AWS Graviton is great, and we've seen a lot of customer adoption. Customers have been super pleased that they can optimize their costs of the EC2 spend, but they want to do more. They want to run bigger workloads. They want to run a broader variety of workloads. And as a result of that, they're looking for more capable instances with more memory, more networking, and more compute cores. And that's where Graviton2 broadens the scope of the workloads that we can run, include web and game servers, open source databases, through to EDA, HPC, analytics. So here's Andy again on stage at reInvent 2019, introducing Graviton2 and the associated EC2 instances, M6G, R6G, and C6G. So comparing Graviton2 to the first generation, we've got 4x the number of compute cores, 5x faster memory for an overall 7x improved performance. So the Graviton2 based instances include M6G, so M is our general purpose family, 6 is the 6th generation, and G is the designator for Graviton2. Similarly, we have C6G, compute optimized, R6G, memory optimized. And these instances provide up to 40% better price performance across general purpose, compute intensive, and memory intensive workloads. M6G is available now. C6G and R6G compute and memory optimized instances are coming soon. And we'll also have local NVMe based instances with SSD storage options also coming soon. So double clicking into the M6G family itself, looking at the sizes and specifications, You see here they're available with between 1 and 64 vCPUs, between 4 and 256 gig of memory, with up to 25 gigabits of network bandwidth and up to 19 gigabits of EBS bandwidth. And these instances cost 20% less versus the equivalent sized current generation M5 instances. So overall, Graviton2's role in life is to allow our customers to lower their TCO, optimize performance and price performance for their workloads. They offer the highest performance within their instance families. M6G is 20% lower than M5 for the equivalent size instances, and up to 40% better price performance versus comparable instances. Ultimately, they offer the best price performance within their instance families. And with that, I'm going to hand over to Arthur, who's going to dive deeper into the specifics of the Graviton2 processor, look at some benchmarks, customer feedback, and the Graviton software ecosystem.
Thanks, Jeff. So we are now going to go deeper into what is inside the Graviton2 processor. So the Graviton2 based instances are powered by the Nitro framework, which is a hardware framework that AWS built to be super flexible as far as the kind of processor we can embed and super fast to introduce new instances. Because Graviton2 based instances are using the Nitro security chip that protects our firmwares from tampering from users, the Nitro cards that are providing a level of abstraction as far as Amazon Elastic Block Store is concerned, providing elastic network adapters and monitoring and security. And it leverages the Nitro hypervisor, which is a lightweight hypervisor managing the memory and the compute resources and providing bare metal-like performances. The Graviton2 is a leap forward compared to the first generation of Graviton processor we released last year. Our first generation was based on a 16 nanometer process. The new one is based on a 7 nanometer process, and we moved from 5 billion transistors on the chip to 30 billion. Doing that, we've reached 4 times more vCPU per instance and up to 7 times more CPU performance compared to the previous generation. The cores that are inside the Graviton2 processor are based on the ARM Neoverse N1 architecture, which is compliant with the v8.2 ARM standard. And we've been working closely with ARM on the creation of the Neoverse N1 architecture. ARM is well known for its mobile processors, and creating a processor for a server workload needs a different design as far as handling interruptions is concerned, as far as size of the caches is concerned. And working together with Amazon knowledge of a data center workload, plus ARM knowledge of designing a fast chip, we ended up with a design with a large amount of cache, 64 kilobytes of L1 cache and 1 megabyte of L2 cache per vCPU, a coherent instruction cache, which is unusual in the ARM architecture, and a mechanism to ensure lower overheads for interrupt, for virtualization and context switching, all of which are super useful in a server context. That core has a 4-wide front end with 8-wide dispatch and issue. It features a dual SIMD units, and it has instructions to accelerate ML inferences. On the Graviton2 processor, every vCPU is a physical core, which means that we do not implement simultaneous multi-threading. So all the data on a core is not shared with any other virtual thread, which is a good thing from a security standpoint. On the Graviton2, the 64 cores are connected together through a mesh, which gives 2 terabytes of bisection bandwidth between the cores and has 32 megabytes of last level cache shared between the cores. If you consider the additional private caches of the different cores, that gives you over 100 megabytes of user accessible caches. Also, the memory topology on that processor is flat, so you will have no NUMA concern. Every core is going to see the same path to the memory and to other cores. So from an application developer perspective, it means that wherever you allocate the memory, you will access it in constant time. It also provides 64 lanes of PCI Express Gen 4, which provides a wonderful flexibility for different instance configurations. At the system level, the Graviton2 processor has 8 memory channels, which gives over 200 gigabytes per second of memory bandwidth. And that memory is always encrypted using AES 256 with ephemeral keys that are generated at boot time. It also provides a compression accelerator with a bandwidth of up to 1 terabyte per second. This device is going to be available starting with 2 XL instances and larger ones, and provides drivers for DPDK and the Linux kernel. The data compression can go up to 15 gigabytes per second and decompression at up to 11 gigabytes per second. Let's look at M6G performance. So M6G is the first instance family that we released based on the Graviton2 processor. Let's look at a first industry standard CPU intensive benchmark, spec CPU 2017. As you can see from the graph on the right part of the slide, we compared M6G to our Intel-based M5 instances. And on the integer part of that benchmark, we can see a spec CPU 2017 performance, which is up to 44% better on M6G compared to M5. And for the floating point part of the benchmark, we can get up to 23% better performance on M6G compared to M5. That benchmark was run on all vCPU concurrently, and we are comparing the performance per vCPU. Let's look at another benchmark when using Nginx as a load balancer. So in this case, we were using a load generator and then Nginx as the load balancer, and behind web servers on either M6G or M5. What we observed when running that benchmark is a 24 better performance on M6G compared to M5 as far as the number of requests per second is concerned. Let's look at another benchmark, this time memcached. So this time we use load generators that are stressing a memcached server on either an M6G instance or an M5. And we can see that on an M6G, we get up to 43% more requests per second from memcached compared to M5. If we were looking to the latency for those requests, we also see that not only we get more requests per second, but the 99th percentile latency is better on M6G compared to M5. We've run an extended preview for the M6G, onboarding many customers to get early feedback. Here are some of the things that our customers have observed. KeyDB, which is one of our customers running a key value database on our instances, has been onboarded on M6G and tested it compared to M5, and they observed up to 65% better performance on M6G compared to M5. Honeycomb.io, which is providing a monitoring framework and observability framework for applications, has also ported its application to M6G. And during the port of their application, they realized that it was really easy to move their application from Intel-based instances, C5 in that case, to M6G. And they completed the port in less than 15 days, not 15 days of work, but just 15 days of elapsed time, for a total of a little bit more than 10 hours of actual work. And now they have migrated the workload from a fleet of C5 to a fleet of M6G, using 30% fewer instances than previously. InterSystems Iris has also ported its software on our Graviton2 based instances. And when doing so, they have observed better throughput on M6G compared to M5. Let's talk a little bit about a database workload. Our customer at ScyllaDB has done some tests on M6G also. They were an early adopter of the A1 instances and were quite happy with the pretty good price performance ratio that the A1 was providing, but A1 was not able to reach the peak performance of ScyllaDB. When moving to M6G, what they discovered is that those instances are really changing the game. All CPU and memory-bound workloads are now supported. The instances are way bigger, so they got a 5x improvement compared to A1. And they're now with M6G close to the theoretical limit that they consider for their database. The bottleneck is now on the EBS side. And the good news is that we will release in the coming weeks instances with an additional instance storage based on SSDs, the M6GD, which is going to make ScyllaDB even faster. A comprehensive review from AnandTech is also available. Those guys have run deep and detailed benchmarks on M6G. So it's always good to have a third party confirming the performance figures that we forecasted. I really invite you to read that article. This is a goldmine as far as performance test is concerned, and you can read it in detail. A couple other feedbacks from AutoBed's Mobius Space and Reagan to illustrate the fact that customers have been able to easily transition their workload from Intel-based instances to those Graviton2 based instances and got better price performance by doing so compared to our existing M5 instances. Let's look at the Graviton software ecosystem. Let's look at the AWS Graviton software ecosystem. So as far as the operating systems are concerned, all the major Linux distributions are available for our Graviton2 based instances. Obviously, Amazon Linux 2, for which we take great care at ensuring that it's super optimized for Graviton2 based instances. Ubuntu is available, including the latest 20.04 version, which brings the best performance as far as Linux, Ubuntu distributions are concerned. You can even use FreeBSD or NetBSD on our Graviton2 based instances. Just Windows is not available on ARM64. In the containers ecosystem, Docker support ARM64 architecture. Our Amazon Elastic container service is available, such as is Amazon Elastic Container Registry. Our EKS service, which is the managed version of Kubernetes on AWS, is available as a preview. And you can also use Firecracker micro VMs on those instances. If we look at the tools and the softwares, most of our tools are available, such as AWS System Manager or AWS Batch supports those Graviton2 based instances. And I would highlight Amazon Corretto, our supported version of OpenGDK is available for our Graviton2 based instances. And we have lots of partners who have adopted the Graviton2 based instances, such as Jenkins or GitLab, Drone.io, as far as the CI/CD partners are concerned. We also have people like CrowdStrike, who has ported its security scanner, Datadog as its agent ported to Graviton2, and many others. So let's now have a look at a small demo. I've been implementing a IO-HTTP-based web application written in Python, something super simple, just a simple hello world. That application is structured so that we have 16 child processes running behind supervisor-D. Those processes are served through a Nginx proxy, load balancing the request over those 16 processes. And we're going to stress the application using the Apache AB benchmark. So I've installed that software on both an M6G 4XL instance and an M5 4XL, and we are going to compare the behavior of both of them. The application is instrumented using the Datadog framework, so we will be able to follow the number of requests per second that the application is going to receive and the performance of both the M6G instance and the M5 instances. Now we are going to quickly log on both instances. So on the right top, you can see the screen of the ARM-based instance, and at the bottom right, you have the screen with the x86 instance. Now let's have a quick look at the code. So I'm connected on my ARM64 instance, but the code is the same on both. Let's look at the benchmark. So this is a pretty small piece of Python code and a handler that is just going to send hello world. Then we detect the platform, configure the Datadog framework, and run the application. Let's switch to the supervisor-D configuration. So supervisor-D is configured to launch 16 processes of that small application, each with a different number, and we are going to serve that through Nginx. So let's have a look at Nginx configuration. So Nginx configuration is configured to send a request and load balance them over the 16 processes, and we can now have a quick look. All the processes are there. So here we have the Datadog agent that is running. And then you can see the Nginx process with its 4 worker processes. And then you have supervisor D and the 16 benchmark application. Now let's launch the benchmark. So first on the bottom right corner on the M5, and then at the top right on the M6G. Now the benchmark is running on both. Let's see a few iterations. So we should see the first one appearing on the M6G. That's done. And now let's move to Datadog. On the Datadog front end, we can see the number of requests per second served by the ARM-based instance at the top, our M6G, and the x86 instance at the bottom, our M5. Okay, so now the M6G has finished its run. We'll wait for the M5. And now the M5 is done. So let's look at the final result. So on the M6G, the full benchmark took us a little bit more than 1,000 seconds. And on the M5, it took almost 40% more with a little bit less than 14,000 seconds. Let's talk about how to transition a workload from Intel-based instances to our Graviton instances. Most of the languages, toolkits, and runtimes are running perfectly on ARM. As far as the AWS tools are concerned, our CLI, our CloudWatch agent, SSM agent are available on Graviton2 based instances. Our SDKs are also available, be it our C++ SDK, Node.js, Python, Go, Java. They're all running on ARM64 architecture. For interpreted and compiled bytecode languages like Python, Java, Ruby, PHP, or Node.js, they can run without any modification on ARM-based instances. Special note about .NET Core. .NET Core runs on Linux and it runs on ARM64, so it's a good candidate to be migrated on our Graviton2 based instances. If you consider compiled application, like those ones written in C or C++, they will need to be recompiled for the ARM64 architecture. However, in most of the cases, they're not going to need any modification, and they will run flawlessly on ARM64 if they were coded in a portable way. Let's look at the operating system images that you can use on our Graviton2 based instances. We have AMIs, Amazon Machine Images, for most Linux distributions, such as Amazon Linux 2 or Ubuntu, available for our ARM-based instances. And you can also run NetBSD or FreeBSD. The container ecosystem is fully available on our ARM-based instances. You just need to pay attention to the fact that you need an ARM64 version of your container image. The majority of Docker official images are already available for ARM64, and the remaining ones can be generated either with Docker integrated building tools or with our code build service. A quick deeper look at the containers. So as I said previously, Amazon ECS is fully supported on AWS Graviton based instances. Our Amazon EKS service for Kubernetes is still in preview, and here's a link for the instruction to use the preview. Our Amazon ECR service, our container registry, does now support multi-architecture containers. So you can upload multi-architecture containers to a ECR registry and then consume it from either x86 instances or ARM-based instances. Our AWS Code Build service also support ARM64 instances, which means that you can compile and generate binaries for the ARM64 architecture, and you can generate containers for the ARM64 architecture. And Docker has obviously support for building multi-arch container with BuildX. In terms of transition strategy, how would you take an existing workload and move that to ARM64? The first step would be to identify your dependencies. You need to identify all the third-party libraries, or be it standard libraries, open source libraries, or paid for proprietary libraries, and check whether they are available for ARM64. And potentially check the provider's roadmap. Most of the open source libraries are already available for ARM64. Sometimes they will need to be compiled specifically for the architecture. And if they don't, be it the proprietary ones or open source ones, and they're critical to your application, please let us know. We are carefully monitoring the AWS EC2 forum, for which there is a link here. Please submit your request on that forum, and we will answer you and ensure that those libraries are ported as fast as possible to the ARM64 architecture. Once you have fulfilled all the dependencies for your application and built your application for the ARM64 architecture, the next step is to test in the infrastructure and to deploy it. It's really important to ensure that all your tests are ported. Potentially, you will have some new ones to write. Perform the usual range of unit testing, acceptance testing, and pre-prod testing that you're usually running on x86-based architecture. And then update your infrastructure as it's needed, be it your CloudFormation templates, your scripts that are coordinating the way you provision your application to your instances. This is probably going to be small, simple changes like modifying an instance type or modifying the name of a package dependency, just to reflect the fact that you're now running on ARM64-based instances. Once you have done that, you can perform a green-blue deployment with part of your workload being redirected to ARM64-based instances alongside with your existing stack. Monitor the error rates, check the user behavior, check the load and other critical factors to see whether that works with those new instances. How to go further? We've published some documentation with recommendation on how to ensure that your application is as fast and efficient as possible on our Graviton-based instances. That guide is available on GitHub. You will find recommendation on how to compile code using the right compiler options. Those compiler options can make a huge difference in terms of performance. So don't hesitate to test and check the results. Also, using the latest version of operating systems is going to help. There have been recent patches applied to the Linux kernel that helps with performance on the Neoverse N1 architecture. So I really invite you to test with those the latest generations. As a summary, our Amazon EC2, M6G, C6G, and R6G instances can deliver up to 40% better price performance compared to the current generation of M5, C5, and R5 instances. Most of the workload transitions are going to be seamless. So check out AWS Graviton2 based instances today and let us know how it goes. Thank you. We are now going to have a Q&A and we will go for your questions.